So in this Excel example for testing for two population variances, we're going to go back to the cola example, beverage placement, where the new cola is placed either near the beverage aisle or the produce aisle, and we had samples, two samples, and we want to test whether the variance of weekly sales of cola for the first placement is the same as the second placement. Sigma 1 squared is equal to sigma 2 squared, or whether the variances are different. So remember, we had sample values given. So let's go to the Excel file. And if you go to sheet 1, this is where in sheet 1 we tested for equality of means for the sales of cola, and here is sample 1 sales, sample 2 sales. Sample 1 is beverage aisle placement, sample 2 is produce aisle placement. So we're going to use these two samples this time to test whether the population variances are equal or not. So the top half of the sheet, we have the general information that we already went over in PowerPoint file. So the three forms of the test, okay, and this is the F test and notations, okay, and we'll usually use the larger sample variance in the numerator, which is not very critical in Excel. Okay, so now we're going to have to define the two sample variances, samples and the variances. So first one is weekly sales. The first sample is weekly sales when we use the beverage aisle as the placement location. So weekly sales with beverage, and sigma squared sub 1 then is the population variance of weekly sales with beverage aisle as our location. Okay. Except 2 is the same with produce aisle as the location, and sigma squared sub 2 is the variance for that location, and we want to test whether the two variances are equal or not. So equal, and the alternative is they're not equal. Now alpha, we'll assume 5% alpha, and the sample size and standard deviations, we can use the information that we've already calculated in sheet 1 and transfer them back here. So the first one, start with an equal to sign, go to sheet 1. So we have sample count, the sample size, and then sample standard deviation is here. Okay, now if we copy it over to the next column, you'll get the corresponding statistics for sample 2. Okay. Now since the samples are small, we have to assume normal distribution for the underlying population. If the samples were 30 or more, then we don't have to assume that. So the F statistic then is sigma S squared sub 1 over S squared sub 2. So this will be, take S squared sub 1, square it, and divide by S squared sub 2 and square that. So that is the F statistic value. Degrees of freedom is n sub 1 minus 1 for the numerator. We used S squared sub 1 in the numerator, and then n sub 2 minus 1, that's the denominator degrees of freedom. The sample sizes need not be the same for the two samples because we are assuming independent random samples. Now the F table value is, since this is a two-tail test, we can use F dot inv dot rt. Okay, we want the right side tail. So in the probability, since this is a two-tail test, we have to go alpha over 2, and then we provide the two degrees of freedoms. The first degrees of freedom is C46, the second one, the denominator, is C47. So 4.03 is the F table value, and we can get this F table value from the back of the book as well, as we saw in the previous video. Okay, so for tail area of 0.025 and degrees of freedom 9 and 9. Once again, the first F table is for a tail area of 0.05. So we need to go to the tail F table for tail area of 0.025, and then 9 and 9 you see is 4.03 right there. So let's go back to the Excel file. And since the F statistic is less than the critical value, we cannot reject the null hypothesis, and that's the conclusion. So do not reject. The p-value approach, so we go f dot dist dot rt. So let's find the right tail. Then remember that we have to multiply by 2 because this is a two-tailed test. So f stat comma the 2 degrees of freedoms, okay, and then we multiply by 2 for this being two-tailed test. So that's the p-value. So the conclusion is p-value is greater than 5%, so we cannot reject the null hypothesis. Okay, now let's do an interpretation. So we do not have sufficient sample evidence to conclude that the variances of weekly sales for the two different location choices is different. Okay, if we concluded the variances are different, then the probability we are wrong, that is we commit a type 1 error, is 24.82%.